questions, please raise your hand, and you give you the microphone, so everyone can hear, because we are registering the lecture and then it will be available on the YouTube. So please ask your questions in the microphone if you have some. So Ton, please, you can start your lecture.
Okay. Isolated here in my little chamber. Okay, so last time we got to beginning to talk about the lattice models.
Tom, can you use the slideshow format?
Oh yeah, sorry, I can do that. Yeah. Wow. Okay, on my big 32-inch monitor here, it's enough light to light the whole room. So yesterday we went over basically classical elasticity in all of its various forms. But what we're going to be principally interested in now for the remaining lectures are lattices that have interesting elastic limits, but they also have excitation spectra and so forth that you know, have topological properties in the end. So I'm going to spend today mostly doing lattice models, and then we will look at the Maxwell Calidine relations that give us really a powerful window onto what goes on in these various lattices that are under constraint. So what we're going to be looking at mostly are these lattices that satisfy the Maxwell Calidine criterion, that the number of degrees of freedom is equal to the number of constraints, which on the lattices really are the springs that go on the bonds. So we're going to start and you know, assign each site on our network. The L can, mostly we're going to be looking at periodic lattices, but you know, the L here can represent sites on a random lattice, a you know, model for glasses and isostatic systems and so forth. So we're going to take RL to be RL0 for the moment. So that's the rest length. That's what the lattice has when it's not being excited, plus a displacement on that. And UL is displacement. So bonds are the material that connect two sites. So the length of a bond, which is going to be important for the length of the spring that goes there, is the difference in the position of the two lattice sites that it connects. So we have an RB0, which is RL prime 0 minus RL0. B then is associated with the bond L prime L. And RB, rather than RB0, is the actual length under extension. And we have that the delta UB, we'll use the notation, is equal to the displacement of the L prime lattice site minus the displacement of the L lattice site. And these bonds then are connected by a potential energy, which is invariant with respect to rotations in the target space. So it's a function of RB, and that is invariant under R Li goes to Uij RLJ. Of course, now I'm talking about that this is not a local rotation, it's a global rotation. So the total energy is the sum over all the bonds of the energy in the springs. And so I only get a contribution when I stretch or compress the springs. And we can write that as a half the sum over all sites L and L prime of the energy of the bond. That B is an L prime L, and it depends only on the magnitude of the difference between RL prime and RL. What's going on here? It doesn't want to obey my, yeah. Okay, so here is some notation mostly. We're going to be looking at, you know, in our minds, we'll have a simple view of the potential. There's a potential part. Remember, this is a spring, the difference between the lengths of the spring and the actual position. Now, I'm not going to insist upon this too much, but strictly speaking, there is a distinction between the equilibrium BR in the lattice and the RB0, which was the equilibrium of the spring. So there are times when you can have tensions in the spring, even though the whole lattice is in a static mechanical equilibrium, and the positions of the atoms in the lattice are not such that that they sit on RB0, or in other words, that the length of the bond, that's what this is not necessarily equal to the length of the preferred length of the spring. But in the end, I'm going to simplify, and most of the time it will be that this is the same thing as RB0. So now I'm going to introduce a quantity which I call VB here for the moment, which is the difference in the squares of the lengths of the bonds. So this is the RB0 squared is the rest length of the spring, and RB squared is the rest length squared, is the stretch length squared. Now I introduce this because what we want is to arrive at a lattice theory whose continuum limit can easily be taken. So this, when we look at this, expand it out, remember delta UB is the difference in the stretches of the sites that the bond connects. So we have RB0 dot grad UB, delta UB, plus a half delta UB. And you can see here that we have, we can smell the fact that when I go to the continuum limit, that this is going to reduce to this part will be the part that is the grad IUJ plus grad JUI, and this part is the grad UI, grad UB term. And then we can expand RB in about the point R0. There's a linear term, which is, if I just take this equation and start expanding it out, I get, RB squared is equal to 2VB plus RB0 squared, and so it has an expansion that looks like this. Now we're just going to go up to quadratic order, but of course, we could, if we wish, go on and add higher order terms, and we can preserve, because this is rotationally invariant in the target space, we can go to arbitrary order. So we plug this in to our VB. So VB has this. It can be expanded, it can be expanded in powers of little VB, and we get the change in the energy, potential energy relative to its rest energy, has a quadratic term that looks like the spring. So this KB is the local spring constant, and the VB squared divided by RB naught squared is in fact going to be our strain, as we'll see in a moment. This term is actually a residual term from possible stresses in the bonds that occur if we have states of, well, I haven't done states of self-stress yet, but this is having tensions in the bond, but an equilibrium lattice anyway. So you can see I have a force dotted into a displacement divided by an area times an area, and this thing has the units of force times distance. And it wants you to think about the stresses being, you have a force crossing a plane, and there is a distance that is between the neighboring points. So we can also use the notation FIL. So this is the force on site L, and it's the derivative of the total energy with respect to the little displacement here. And it will be the sum over L prime of the force exerted by the bond on L prime. Most of this will become pretty transparent as we proceed. Okay, so we're interested in various limits. One of them is the harmonic limit. So in the harmonic limit, we have a contribution which is V double prime EB0 EB. So EB is the stretch of the bond. Recall that's what we discussed that earlier. And then we have this part that is 1 over RV prime, and that's what comes in when we have some stretch, equilibrium stretch in the lattice. And then of course, it's going to be proportional to delta UBI, delta UBJ. So this is the amount that the bonds have been stretched This is the UBI, or the delta UBI is what did I call it? Well, UL minus UL prime. So the harmonic energy, when we assume the VB prime is 0, and we'll do that most of the time. I mean, it's a whole different course when you include this term. So throwing this away, we have that the energy is an elastic constant, which is the VB double prime. Remember, if I have a harmonic oscillator, the second derivative gives us the spring constant. So this is the spring constant of bond B, and we have the EB0 dotted into the delta U's, and then we can go back and convert the B's back to L's, and we get this harmonic equation, which you often write down without thinking of the preceding considerations we were talking about. We have Ui of L, Ki j of L prime, Uj of L prime. And at this point, this applies to any lattice, some model of a glass, quasi-crystals, what you wish. So it's not necessarily periodic. However, if we think about periodic lattices, then we want to talk about lattices that are not just a single site lattices. We want to have lattices which repeated unit cells, whose marking point is the L we had before, so that could be the position somewhere in the unit cell, and then mu labels the additional atoms in the unit cell. In which case, going through this procedure, we can get the harmonic energy and writing it out in its glory. There's the stiffness tensor now has springs between mu and mu prime and as well as L and L prime. And now we have a periodic lattice, so we can do a Fourier transform, and this is a quantity which we'll be working with a fair amount. From this, of course, we get the dynamical matrix by dividing the stiffness matrix by M. Now, of course, what I'm assuming here is all of the masses are the same. We could introduce an extra layer of complexity by introducing different masses for each mu, in which case this M will be replaced by the square root of mu prime, but we will not be doing that. Now the continuum limit, basically we take the RL0 and think of it as being the X, and the RL of R sub L goes to R of X, and UL goes to U of X, and VB becomes RB0 prime Uij, where Uij is grad U, this is exactly what we had before. So by using the B, we introduce the nonlinear rotationally invariant strain tensor here. We have sum over lattice sites. That goes to an integral over the volume. See, L is basically, doesn't have length. It's just an indicator of a number. So that becomes integral d to the dx s of x divided by v of x. And from that, we can then extract the elastic limit of the free energy. It's a half times the elastic tensor, which we could allow to depend on x itself, times uij of x, ukl of x. And this sigma ij of x is telling us what the stress tensor is at a given point. So we said that it's the forces from this stress tensor, when we integrate it over all of space, is 0 because the internal forces are not going to cause the whole body to move. So this is, for the moment, the captured stresses in the system. Now, what is peculiar about this treatment is that when you calculate the Kijkl, the elastic tensor, it has the 1 over v of x, which came from changing the L to a volume, the spring constant of each bond, times a tensor, which is RB0I, RB0J, RB0K, RB0L. And this thing has more symmetry than the general argument we had about the elastic tensor being invariant under interchange of I and J, K, and L, and of the I, J, K altogether. This one is invariant under any interchange of all the L's, and so this is an incomplete theory in terms of what the possibilities are, written in this particular form. if you have many atoms per unit cell, this does get modified, and you have non-affine distortions of the sites inside the unit cell. So we won't necessarily be using this in too much, but it just shows where the continuum limit takes you in the initial steps. Okay. So Continuum Theory Two, this is a repeat of what we just had. So one, this is rotationally invariant because the energy depends only on the nonlinear Uij of x. And the standard, I guess this is a repeat of what I just said. What we found was that Kij, Kl obeyed all of these changes in the indices, and there's an equality between these. What we add are the so-called Cauchy symmetries, where Kij, Kl is equal to Kikjl. So that's mixing up, up here we're allowed to interchange K and L and I and J, but we're not allowed to interchange I and K. So that reduces the number of, up here, there are 21, the most asymmetric solid has the possibility of having 21 different elastic constants in 3 dimensions. This symmetry, additional symmetry, reduces the number to 15. Okay, so now we're going to move on to the marginally coordinated lattices, the Maxwell-Calidine theorem. So these are the lattices that I want to call, or do call Maxwell lattices. They're the ones where, under periodic boundary conditions, dn is equal to nb. So just a little bit of history. In the 1800s, the Industrial Revolution was in full bloom, and you were able to see for the first time bridges like this. And James Clerk Maxwell had asked the question, under what circumstances are structures like this stable? And so his idea was that you can look at the positions where these struts meet. You can think of the struts as the bonds. And he says the lattice is stable, or the configuration, if each of these sites has no force on them. In other words, that they are constrained by the stretching or unstretching of these connection trusses. But for us, even though this is used for enormous architectural and engineering things where the scale is on a human size, today we can make all of these other lattices using various techniques, additive manufacturing, various cutting things. It's really amazing the number of things you can make at the 10 micron scale. So here is this is the pyrochlore, the pyrochlore lattice. Yeah. And this is the full version of it. So these kind of things will be our treatments are relevant to. So the Maxwell count. So the bridge is a frame with sites that are connected by trusses or bonds. The sites each have dn degrees of freedom in d dimensions. So I'll use the abbreviation DOF. And the struts impose constraints on them. Maxwell's argument was oops, wait a minute, go back again. Oh, I see, I can't correct it here. I thought I was gonna correct. This should be that to be stable and stationary. The number of bonds must equal the number of degrees of freedom minus the number of rigid translations and rotations, which is d times d plus 1. So he said that NB had to be dn minus WD. And here is a cartoon of the strut. So you have all of these sites and lattices on a lattice, but you need to constrain the motion with some external forces to keep this thing from falling apart. So what you do, and this is actually done in real bridges, you nail one end here, so that it can move neither up and down or back and forth. And then over at the other side, you constrain the site so it can go up and down a little bit. I mean, back and forth a little bit, but it can't go up and down. And in fact, if you look at a bridge, you'll find at the end they usually have a set of rollers so that the expansion of the trusses is acceptable, but moving up and down is unacceptable. And even the simplest version of a Maxwell-like lattice, this one here, where I've just taken this part of the Warren truss, you have to, in order to see what the mechanisms are in this, or what the degrees of freedom are to rotate freely. So here again, you nail this one down and you allow this one to go back and forth to see what happens on the rest of the system. So again, as I said, what we're going to be interested in are Maxwell lattices. And these are lattices in which the NB equals dn constraint under periodic boundary conditions is actually obeyed. We don't have to worry about putting in extra forces to get the perfect balance of constraints versus number of degrees of freedom. So, here are some example lattices. Here's the standard Kagame lattice. Notice that it has straight lines of bonds that traverse the whole sample in 3 directions. But there is an elastic instability, which we'll discuss in a moment, which allows you to take this lattice, rotate it and distort it in various ways so that you preserved the Maxwell relation of NB equals dn, but you have a different structure altogether, and just to show that you have more than one. This is what I refer to as the twisted Kagame lattice. And this is a twisted Kagame lattice, but it has a bigger unit cell. It has all of these. It has 1, 2, 3, 4, 5, 6. I think it's 6 atoms inside the unit cell, whereas this one only has 3. The 3 atoms at the end of the triangle are that. And so now we look at the square lattice here, that you have straight lines of bonds again, just as over here, which is giving it a resistance to compression. But the shear is trivial. I just take the top and pull on it and allow it to its total length in the vertical direction to diminish. But this can be distorted as this one can. So here, all we've done is, well, we could have left them as squares and do this, but it turns out it's better to change the length. These are all in the same theme as the square lattice. So these lattices will have more exotic topological effects. In fact, rather than having topologically protected edge modes, which they do, they also have topologically protected vial modes, which are points in the lattice where the dynamical matrix has zeros. Oh, here's some more. These are more 3-dimensional ones. This is the Pyrochlore lattice. Notice that you have you can count 1, 2, 3, 4, 5, 6 bonds that hit each site. So the total number of constraints is the NB is equal to dn. But you can take this lattice and change the lengths and so forth. You still have a Maxwell lattice. And the difference between these two is, this has interesting zero modes on the surface. This one has extra lines that traverse the sample, and therefore it has some more rigidity in directions that this one doesn't have. Here is a picture of quasi-crystal lattice. Excuse me here. And it's showing what we call states of self-stress, which we get to in the next slide. So let's now look at some Maxwell rule analysis of some simple examples. So here is a network, if you wish, that has 6 sites and 7 bonds. So the number of zero modes is equal to the total number of degrees of freedom, which is 2 times the 6, minus the number of constraints, which is the 7, and that's equal to 5, which we learned at some time in our grade school, is equal to 3 plus 2. And what that tells us is we have the 3 rigid translations and rotations of the whole object. And then we have soft modes, which in this case, which are called mechanisms. So the mechanisms are the zero modes that come from distorting the lattice as opposed to translating it. So this one has, no constraints on it, and it can move back and forth. Now let's add another girder here that connects these 2 points. So that adds another constraint. So we have NC is equal to 8. And then the total number of zero modes is 12 minus 8, which equal to 4, equals 3 plus 1. There is one mechanism that's depicted here where I can just shear this square like that, which is the same sort of motion we had over on this side. Now add one more, put it here. We now have, again, 6 sites, but 9 bonds. And N0 then is 2 times 6 minus 9, which is 3, which means we don't have any extra mechanisms involving zero energy distortions of the lattice itself. But you look at this and you say, well, you added one more bond. Why can't I add a bond this way? And you can indeed. If you do that, you introduce a mechanism here, in other words, a zero mode. And if we do the count, the number of sites is still 6, the number of bonds is still 9, and N0 is equal to 2 times 6 minus 9 equals 3 in this case, because now, I'm sorry, we did this one. And the 6 minus 9, 12 minus 9 is equal to 3 plus, what it's not. The number of zero modes is equal to 3 plus 1, because I have this zero mode, and m equals 1, so we've violated the relation that dn is equal to nb minus the number of rigid translations. Something's wrong. So what's wrong is that this has another property. It can have tensions in the bonds, which is what these arrows indicate, with, excuse me? Is there a question?
It was not, Tom.
Okay, no. So here, the tensions in the bonds are such that the forces on the sites are 0. So that's perfectly permitted. It's an equilibrium. So we need something else to describe this. So what we've done is add what Calidine called a state of self-stress. It's a situation where you have bonds that are under stress, but the forces on the sites are 0, and we have one of those. So the suggestion is that we should modify the N0 equals dn minus nb, keeping track of the W of D in the way we discussed. So we now have a relation N0 minus ns is dn minus nb. And this applies to the Maxwell lattices, where we don't need any extra forces to worry about them to keep the system in place. Okay, so types of mechanisms. There are 2 types of mechanisms. These are the zero modes that involve a change in the structure. So this is that shearing mode. Here we start with a parallelogram that looks like this, and you can distort this site and move it over to there, and this site comes down to there. So this one has one mechanism, and it's a macroscopic mechanism. It's not infinitesimal. This one, however, is infinitesimal. So what I have is a spring that connects the 2 sites 1 and 4, and then springs that connect sites 1 to 2, 2 to 3, and 3 to 4. And what we're talking about now is what happens if I try to move this upward. Well, that requires that the forces that this feels when I move it upward is proportional to the square of the displacement rather than linear in the displacement. So that's something that the linear theory we're talking about does not accommodate. It really is not, it's not a macroscopic mechanism because I can't really move this an amount that I can actually see, but it's nonetheless in the arithmetic that you do for the linearized theory, it will emerge as a zero mode because this thing gets displaced upward in a way that the linear theory cannot see. Other states of self-stress, you can put this together in a hexagonal pattern, and if I close the loop like this, all of these springs are under tension, and none of the particles have any force on them. Another one is this line, which I'm thinking of as being in periodic boundary conditions that we use in the calculations. This one is the same as that one. So this configuration really is the same as this one. And we have only in this case, we have the infinitesimal zero modes that go upward. So you can have more complicated structures. Here, this we still think of as being under periodic boundary conditions. So this line is the same as that one. But notice I can apply stresses of different signs so that the total force on this guy is zero. It's pulled downward by the two springs at an angle, but the vertical one pushes upward and its force is equal to twice the force of one of these times the cosine of this angle. And so every one of the sites is, it has a zero force on it. And again, we have the infinitesimal displacements. So just to go over it, A has one finite mechanism, two translations and one rotations. This one, the B, has one state of self-stress, which is the one that goes with putting tensions in these bonds so that the total tension in this one is equal to the tension in each one of these, and there's no force. The C and D under periodic boundary conditions have one state of self-stress, as does this one. Now, that's pictorial. It's actually a rigorous theorem, which I'm going to go through here now. This is the genius of Calidine. So we're going to take this sort of simplified F, or I don't know, I forget which font we use, but this F is going to be a vector in the D n-dimensional space, the F, of the D components of the forces of each lattice. In other words, this is a D n-dimensional vector, and it lives in a space VF, we'll call it. External loads are determined by the D n-dimensional vector L, which in equilibrium is equal to minus the internal forces in the system. Let T be the vector of the NB dimensional space in the NB dimensional space, BT, of the bond tensions. And U to be a DN dimensional vector in the space VU of site displacements, and E is the vector in the NB dimensional space of bond elongations. So the tensions determine the forces F, and there is a dn cross nb dimensional matrix Q connecting the two, right? So we have QT is minus F is equal to L. So this is an algebraic relationship, which is true by construction. Similarly, we have an NB by DN dimensional matrix, this C, that takes U to E. And again, it's by construction. So Q is called the equilibrium matrix and C the compatibility matrix. This is the language taken from the engineering community from which I learned most of this. The physicists have other terms which are not at the tip of my tongue at the moment. So now we have a relation amongst all of these. We want to know if there's any relation between the U's and the T's, etc. And what we're going to do is to look at the virtual work. The work done by the external load must equal the work done, WT, done by the bond tensions. So the work done by the external load is the force times the displacement. So if I wrote this out in components, we would have the force on each site times the displacement of each site is equal to the contribution to the total work done by the external load. Now we learned that QT is equal to L. So I have this up here, QT. Let me move this guy up a little bit. There we go. QT is equal to L. So this becomes T transpose Q transpose U. And that has to equal the work done by the internal tensions. So the work of each bond is equal to the tension in the bond times the stretch of the bond. So we know that E is equal to CU. So now we can see that T transpose Q transpose U is equal to T transpose CU for every T, for any T. So that can only be true if C is equal to the transpose of Q. So now we have to appeal to some theorems from linear algebra. I'm sure that most of you have forgotten a lot of this. I'm not going to rederive them. But what we're going to look at is how the various dimensions of the spaces that are created by these relations relate to each other. So the null space of Q is the space of vectors T such that Qt equals 0. And you can see why that is. Qt is equal to L. And if there are no forces on it, then T is an acceptable set of tensions, which appears in the states of self-stress. We can apply tensions with no force. So the null space of this, often called the nullity, is the dimension of the null space of Q is equal to the number of states of self-stress from this relation. Then we have the general relation for linear operators or matrices that the rank of Q is equal to, plus the nullity of Q is equal to NB, I always have to think to make sure I get the direction straight. NB is this is the Q is a dn cross NB matrix because it takes tensions into forces. So this is the dimension of this operator. Let me just think a minute now. Did I miss something that I wanted to say? Right. Okay. And so the rank of Q is the rank of the orthogonal complement, which I denote in some places in a moment as OC. It's the orthogonal complement. So this is the rank is telling you the number of degrees of freedom that you can actually manipulate with. The NS is telling you about the 0 part. And there's a theorem. Okay, so we've done the Q part. The C part has a similar treatment. The null space of C is the space of vectors U such that CU is equal to 0. Remember, CU was equal to the stretches, and the null space is the space of displacements that give us no stretching of the bonds. So the dimension of the null space of C is equal to N0, the number of 0 modes in the system, or whatever their origin. So again, we have rank C plus nullity C is rank C plus N0 is equal to Dn. In this case, this is the dimension on the right-hand side. So now, given that the rank of the two are the same, we can write it like this: rank plus nullity Q is rank Q plus NS equals NB. Rank C plus nullity C is equal to rank C plus N naught is equal to Dn. So now I can subtract these two, and I get, using the fact that rank Q and rank Q transpose are equal to each other, what we get is nullity Q minus nullity C is equal to NS, or rather nullity. Let's look at this one. We subtract these two. We subtract the NS minus NB from M0 equals Dn, and we get N0 minus S is Dn minus NB. So this is what we got looking at the pictures, and it's very important. It tells us that if we know the number of zeros and the number of states of self-stress, that must be equal to Dn minus NB. And this is a general relation that doesn't apply. It doesn't apply only to Maxwell lattices. moving on here. So we've looked at the general properties. Get a drink of water here. My mouth gets dry. We've looked at the general properties of the whole lattice. Now let's look at the periodic lattice with a basis. So now we can do a Fourier transform. And when we do that, we find that after we do this property, so I will get to that in the next slide, right? So we have a general periodic lattice with NC unit cells of little n sites and little nb bonds, so that the total number of sites and bonds are respectively, the total is equal to the number of unit cells times the number of sites in the cell, and NB is equal to the number of unit cells times the number of bonds. We can now write the displacements of the site L, the site mu in unit cell L as R sub L, which lies on a Bravais lattice, plus RU and RB, which are different. The positions of the centers of the bonds are different from the sites in the lattice. So L is L1 up to LD. The positions of RL are this set of numbers times the primitive translation vectors in the system. This is straight out of solid state physics. And we can do the Fourier transforms, and they can be, you can either include the RU and the R beta displacements in the definition of the Fourier transform, or you cannot. It's your choice, and sometimes this one is better, and sometimes it's better to leave that.
Tom, we
Once
have a
we
question.
Have that, we're going.
Tom, we have a question here. Let me pass the microphone.
Yes.
Hi, Professor. Thank you for the lecture. What are the differences when we say a Maxwell lattice and isostatic lattice?
Is a static lattice.
Yeah.
Well, the Maxwell lattice is the, if you wish, the reference space of the elastic system. Okay, except the points are on a lattice and not on a continuum. And so it's, the Maxwell lattice can be distorted, and it's the distortions that we're talking about. Is that clear?
Yeah, but I mean, there is a difference in the number of balance between degrees of freedom and restriction when we say is a static lattice and Maxwell lattice, or is the same? Is the same concept, or are?
No, the reference lattice, which we're calling a Maxwell lattice, can be distorted. It remains a Maxwell lattice under the distortion, so we will be able to discuss the dynamics of the displacements relative to the equilibrium of the Maxwell lattice.
Okay.
I didn't quite understand one of the words.
He's asking about the difference between the isostatic lattice and a Maxwell lattice.
Oh, okay, isostatic. Okay, so this, under periodic boundary conditions, you can safely call this an isostatic lattice. Now, the engineers have a slightly different definition of the isostatic lattice. But for the physicists now, we've come to say that the isostatic lattice is the one in which the number of bonds is equal to, what is it, a half C times the number of Z times the number of sites. And the Maxwell lattice is that, but I wanted to use Maxwell lattice because I didn't want it to be, as a definition, it doesn't, the states of self-stress can modify the two. So it's not simply that you have, well, what the engineers would say is that you have to have that both the null space, both the both the number of states of self-stress and the number of mechanisms must be 0, I think it is. In other words, you know, you have the relation that, let me go back here. Let's see. I should have come prepared for this. Yeah, so you want that the both QT and CU are equal to 0 is what the engineers call the states of self-stress. I mean, could call the isostatic system. What we in the physics community have come to use is simply that the number of, that CU is equal to 0 and not the QT is equal to 0. Okay? In other words, I think that strictly speaking, in the glasses or in the you know, sand piles, you can have bonds under stress even though the net forces are 0. And the definition that you know, that CU is equal to 0, or that dN minus NB is equal to 0. Let's see. Here, if you say that dN is equal to the number of bonds, that's the physicist's definition of isostatic. But you know, that's equal to 0. But is it equal to 0 because the number of 0 modes are 0, or because there are states of self-stress as well? And that is not treated or acknowledged in the definition the physicists use. That clear?
Yes. Okay. Thank you.
Yeah. Oh, shoot, I have to do it like this. Okay. So now, you know, we've diagonalized the Hamiltonian by introducing this Fourier transform, and the matrices break up into blocks for Q. So you know, I don't have any communication between Q1 and Q2 in the matrices that we have. And we'll come back to that in a minute. So I just wanted to say, you know, if we have a basis, we have this, and I will have more to say about it in a minute. So let's just do a simple calculation of the C for this. So our task is to calculate C for the frame B. Now, we mentioned that, well, you know, here you can write out all of the things. What is E1? E1 is the unit vector along bond 1 times U1 minus U0, and so forth for all of these. The forces are, you know, the force at 1, force at 0 here. Both of the arrows are pointing away. And so this is T1 plus T4 is what the force on 0 is. The force on 3, for example, now has 2 vectors going in and 1 vector going out. So it's T3, which is going to the right with an arrow. And the other 2 have arrows going in, minus T4, minus T5. So these are all of the relationships that come out of the Maxwell-Calidine discussion. So we have an 8x5 dimensional compatibility matrix and a 5x8 dimensional equilibrium matrix. And that gives us a little bit of a problem when we're discussing what the mechanisms of this type of structure is. And it's really better to go and say, well, let me doctor this up so that I do the same thing we did for the you know, the bridge we were talking about, to clamp this one down and allow this one to go back and forth, but not up and down. So that reduces us to 5x5 matrices. We've got all of these things written out here. I think, remember, you know, I think I don't have to say any more about what these are. Just T beta is the magnitude of the tension times the unit vector in the direction of bond beta. So this is a bond property. E beta is unit vector along the bond times the differences in the displacements of the 2. Okay. So now what we're going to do is to, you know, get rid of the spurious displacements down here. We've locked it in, so there are forces which we don't know, but we know that they have the job of keeping this fixed and this one to go back and forth only. So U is U1x, it allows the x direction, u2x, u2y, u3x, u3y, and that's the 5 different degrees of freedom we're going to be dealing with because we've frozen the other 3 out. The tensions, we have 5 bonds, so that is just E1, E2, E3, and E4, but rather these are the strains on the lattice side. These are the stretches of the bonds. The T are the tensions in the bonds, and the forces that go with this, we don't have to worry about the x and y components of the 0 force here. We know that adjusts just to keep it fixed. And so it becomes F1y, F2x, F2y, F3x, F3y. And so you can write out the equations on the other page that we just looked at. So this is the E equation and the T equation. I'm just writing those now, these equations out, and you can convert that into the matrix CU is equal to the stretches here, and this is the C matrix. Now, I leave as an exercise to you, use the QT equals L, which is the F thing, use that to calculate the Q matrix, and then show that the transpose of the Q matrix is in fact the same thing as this. Okay, what are we doing for time? Marching right along.
You still have half an hour, more or less?
Half an hour, yeah.
Yes.
Yeah, no, we're in good shape. I've slowed down a little bit. And okay, so now we're going to look at the Maxwell. So we've diagonalized and decoupled a lot of the sites. And now rather than having C capital U is equal to the E, for each Q, we have a C matrix and a Q matrix. And all of the general statements we made apply to the Q as well as to the grand ones. So we have that the number of 0 modes at wave number Q minus the number of states of self-stress at wave number Q is equal to dn, where n is the number of sites in the unit cell, and n sub b is the number of bonds in the unit cell. So n0 is the number of n0 of Q rather is the number of zeros. S of Q is the number of states of self-stress. This comes from the Maxwell periodic lattice. Now, okay, so let's look at the Maxwell periodic lattice now. By construction, the lattice has dn equal to nb. So n0 of Q minus ns of Q has to equal dn minus nb for every Q. So that means that, since we have dn minus nb equal to 0, the number of 0 modes at wave number Q has to equal the number of states of self-stress at wave number Q. And that really is a strong constraint that tells us a lot about what kind of phonon structures we can have in the lattices. So you can see now if I have the null space, well, okay, I think it should be clear what we've done there. So now I want to look at the dynamical matrix and other things, again, expressed in this new language. So the elastic potential energy and the harmonic limit can be written in the following form: a half E times the diagonal matrix of spring constants times E, and that's equal to 1/2 U times the capital K. The capital K is the stiffness matrix times U, which we get by replacing E by CQ. So K then, this capital K is Q little k Q transpose, or C transpose KC, since we know Q transpose is C and vice versa, and D. So this then gives us that Q. Now we have this is true for each value of Q, and K of Q is equal to M times the dynamical matrix. So we've got the dynamical matrix once we've calculated either Q or Q Hermitian conjugate. So if one way you could actually calculate D rather than doing it in a more step-by-step basis, if you know what the Q is. And K is the NB by NB diagonal matrix And so our equation of motion is that mu double dot, so this is the full matrix U, is minus the derivative of the potential energy, the elastic energy, plus the external load force, which becomes minus Ku plus L times. Now, an interesting thing here is that when we calculate the force on the site, we don't have to worry about the problem of the Voigt versus standard representation of the elastic energy. This is perfectly fine. There's no ambiguity about the U, which there is when we look at the strain variable, little u. The kinetic energy is a half m u dot transpose u, and our Lagrangian is this thing, which is, has lots of degrees of freedom in it, compactified into a little line. And the equation of motion is mu double dot is dvl ut, which is what we got down there. The elastic energy now in the Q space now looks at the bonds in the unit cell, and the elastic energy is stretch transpose spring constant matrix E, which then becomes ut k of qu, and the k of q again is m times d, and this is what one used to calculate the phonon spectrum. Let's see, do I have this in the right order? Let me just look forward here. Okay, so I want to, eventually I'm going to be talking about what the elastic energy is. So I'll just remind you what we have. I mean, it's a little bit of C of notation, but I think we need to look at it. So I want to look at the, first, what an affine strain is. So the affine strain is the percentage of a change in bond lengths are all the same. So I have an x of s prime minus s. So this is the stretched difference between the stretches, the displacements of site s and s the other. And that's equal to lambda times the bare. So lambda times the, so we're using the notation now that R is the rest equilibrium position, and capital X is the distorted position. So lambda is equal to I plus eta. I played around with, there are too many variables here, so I just thought I would try putting a upside down half circle on these to indicate that they are matrices. But so lambda we learned is I plus eta. Remember, this is grad with respect to the x variable of the u displacement, and this is then multiplying the distance between the equilibrium matrices. And this translates then into u of s minus u of s prime, or u of s prime minus u of s, is the eta matrix, which remember is the linear displacement matrix. And so that is equal to eta times the vector connecting, the rest vector connecting s to s prime. It's the bond length, the bond vector of the bond B. And the affine distortion then comes from dotting that into remember that we're talking in the continuum limit, and the only thing that's happening to the bonds is that they are stretching. So this gives me a vector of some length pointing along the bond length, and what we're interested in is what the magnitude of the stretch is, so we just multiply it times the unit vector along B, and you get this expression. So the energy associated with an affine distortion is simply the same thing we had before, E k transpose k v, but the affine distortion is simply this, where all of them are the same. Now, what we want to do is to consider what happens when we have unit cells that are bigger, or the possibility of having response of many of the sites be different from E affine. We apply the affine distortion, and then we calculate the displacement of all the sites. In other words, the affine distortion causes displacement of the sites. And then we end up with an energy where we've taken into account those extra sites, and we get the full elastic energy, which is comes from a macroscopic distortion at the edges and lots of little things going on in the middle. So we're going to take, rather than E affine, we're going to take E is equal to E affine plus a part QTU, which remember gives us E before we've had the affine. We fix the E affine and then we allow this to relax so that we minimize the energy of the whole system in the presence of the E affine. So this is a little bit heavy. I believe I put it in the notes that you have. What we're going to do is to take our matrices and break them up into a part along the kernel of Q. Remember, that's the set in which the Q's are mapped to 0. The QT is mapped to 0. And this is the orthogonal complement. That's the rest of the space. And we're going to take define projection operators onto those two spaces. So I see the notation I should have changed here. The PQS corresponds to projection onto the kernel, the PQR onto the orthogonal complement. So I can write QT, for example, and I can transpose it. I can break it up into parts RR. These are all of the components lie in the orthogonal complement. QSS, all of them lie in the kernel, and then you have the cross multipliers. So we can now, that's the wrong direction. So QT times U is the QTRR plus QTSR times UR. So all of these are in the orthogonal complement, and the reason we can eliminate all of the others is that they have a vector. The column vector is in the matrix actually lives in the null space. So any vector I put over here kills the part that's in the null space, and we're left with this. Similarly, we can, this QTR is a vector now in the kernel of C because QTS is that. So if I multiply this operator by any vector in the kernel, it kills this part. So the net result is that when I look at the energy, the elastic energy, which had an ET affine, it breaks up into a part QTURR. So we lost everything except the RR part of this and the TT part. And then I can minimize over the UT that's left, and we get that, assuming the QRR is it's invertible. So we get QRRK times E affine plus this additional part is equal to 0. Now this is true for all K and QRR, so I can take I can just kill the QRR, but the affine part has a part that is along the S direction. So I write this as let's see, did I write it up here? As E affine R plus E affine S with a K, and the K has an RR and an SS part, RS part rather. So I kill this guy, I have KSR plus KRR on E affine plus this. So the KS part doesn't operate on this because this is already in the R direction, but it can operate on the affine. And the net result is I can now replace the E affine by E affine R, rather this part as E affine plus the QTR, all in the R direction. And then I have what comes from this in the S direction. It's the KRR inverse times KRS. And now I have an expression for the S part of E affine in terms of the R part. So taking the, so now I want to replace the E affine by E affine itself, and then This is linear in E, so I can put it all together to get this expression, which is kind of daunting, but it's E affine S K inverse SS inverse. And notice now that we have an expression for the energy that only sees the components of E along the states of self-stress direction. Only the S part appears there. So that makes sense that the elastic energy, you don't see any elastic energy unless I've done some stretching, and that then requires that I be in the null space of Q. So this now gives us the full elastic energy of our system. And so this operation just shows that this combination that we had of the KSS, KSR, etc., it's equal to the inverse of the inverse. And in the end, if we have all of the elastic constants are the same, this whole expression becomes the affine distortion dotted into the unit vectors in the space of the kernel of Q, which is the QT is equal to, let's see, Q times, yeah, Q times T is equal to E. No, the other way around is equal to T. Well, okay, I'm getting scatterbrained right now, but the kernel of Q is the null space of Q. And so we know now that the dimension of the null space of Q, because we have dn is equal to n0, and we know what dn and n0 are, we know what all of the variables in the kernel are, and we know that the kernel is a two-dimensional matrix. So let me just see here, go back to this expression. We have these dn equals nb, and n0 is equal to the number of states of self-stress. So we've calculated, the number of states of self-stress is equal to 2, because that's the only, that's what we get out of doing the calculation of ns. And that means that we have, am I going backwards? I'm going backwards. So what does this tell us about the elastic energy? Remember that, let's just think in two dimensions. We have, in 2 dimensions, we have only 3 independent strains. In order for the system to be stable, we have to have 3 different combinations of the squares of those. So what this leaves us with, since this is only a 2-dimensional T, it leaves us with 1 zero mode in the elastic energy. And that's what we call the Guest-Hutchinson. So the so this is what we were saying before, that the n0 of Q is equal to ns of Q. N0 of Q is equal to D. That's the number of zero modes, and that's equal to 2. The only zero modes we have left are the translational modes, and this is at Q equals 0. And Q equals 0 corresponds to an elastic limit, and this is less than the D times D plus 1 over 2, telling us that which is equal to 3 in 2 dimensions. So this energy is a 2-dimensional energy, and it gives us 1 Guest-Hutchinson mode for in the elastic energy. Let's see if I wrote the next one. Yeah. Okay, I think I forgot to include the, well, wait, just go 1 second here. Yeah, okay. I'll show you another picture of a series of distortions that you can do on the Kagame lattice. next time when I remember to put it back in here. Okay, but anyway, we've now got that there has to be 3 zero Guest-Hutchison elastic distortion modes in 3 dimensions and 1 in 2 dimensions. Now, that tells us something about the zero modes of the bulk, because you know, if I go to the bulk with Q slightly larger than 0, the UXX becomes IQX where Q is, you know, of course, the wave number. The YY is IQY, and the XY component mixes the two. And what you can say, I mean, you can take this and ask, can I calculate what QY over QX is? Well, we know that the ratio here I mean, just from these equations, we can find that UXY is equal to 1/2 lambda, where lambda is the ratio, UYY over lambda. And I can replace the QXYs by, well, you can take this now and calculate what lambda is, and it's this expression right here, which this lambda now tells us something about the decay of surface states. So let's let, I'm a little confused now as to what I wrote. Somehow I think I missed one of the, yeah, okay. So anyhow, the lambda, if I take a sample with, maybe it might be better for, yeah, so let's take the X direction to be along here and the Y direction to be like that. And so I want to know if I have a mode that's a mode on the surface. Well, if I have QY over QX, an imaginary number, then e to the IQY tells me that I have a decay of the mode going into the bulk. So now let's go back to see what we've got here. So this says that QY over QX is equal to this lambda, which is this, and there are two possible values. Now notice that if the determinant of UGH, so that's the determinant of this matrix, which we can calculate because we know what the stresses are. If they have imaginary, if it's greater than 0, then there's a minus sign here, and both lambda plus and lambda minus have imaginary parts, giving rise to edge modes that decay exponentially into the bulk with an inverse decay length given by this value. On the other hand, if the determinant is less than 0, then this turns out to be real, and all we have are bulk modes. But, you know, we've been talking about 0 modes here, and it turns out that we do have a mode, but its energy or frequency is proportional to Q squared rather than being exactly 0. And you can do that calculation, and we try perhaps to see examples of it later on. So that brings us to the close of this lengthy detour onto, you know, properties of Maxwell lattices. So now let's look at some specific Maxwell lattices. Let's look at the Kagame lattice by itself. See, it has these straight lines of bonds. Now think of putting this thing on a torus. So this point would be connected to this point would be connected to this point, right? So I draw a triangle right here under periodic boundary conditions. And what that gives us is these circular patterns where there's a state of self-stress for each line of bonds. And I can then ask, well, what does that tell me about what kind of modes will I have? So first of all, we know that for each state of self-stress in the Maxwell lattice, there is a 0 mode. So what that's telling us is that there is a zero mode for each one of these lines that go like that. Well, those that are, you know, under the compression. So if I'm looking at the bulk modes, I can use the periodic boundary conditions. We can also ask, well, I think I'll delay that to the other. So what we want to look at now is the energy spectrum or the frequency spectrum of this lattice. And here it is. You have, I should say, these red triangles are telling us what the zero mode associated with this lattice is. Remember, what we're doing is moving these points which are along a line. Well, you see along a line like this, I have these points on the line under a system that's under tension, and I can move this up an infinitesimal amount and not introduce any energy. So this is a zero mode when I stretch this a little bit beyond the straight line. So now what we have is the frequency of the modes is given by this. We have 3 modes coming into 0 along the line m to k. And along the line gamma to m, we have a line of 0 modes. So for every q along here, there is a 0 mode, which is associated with one of these lines of stress. And it comes in with a knife edge. The frequency comes in like, you know, a knife edge, and it's along all of the symmetry directions, gamma to m that way, and gamma to m that way. So really, you know, just looking at the qualitative features that come out of looking at these Maxwell lattice systems, you can tell a lot about what the energy is. And I notice that there are also, normally we would expect only 2 zero modes coming in here, but at q equals 0, we've got the Guest-Hutchison mode, whereas down here, you know, it's just 0. Okay. Now, what happens if I twist the lattice? So here's the twisted lattice. Now I've lost all the straight lines, so there are no 0 modes other than the trivial ones of translation under the periodic boundary condition. And if I, you know, do a cut up here, which we'll discuss in a moment, we'll see that this guy actually has surface modes, whereas the other one doesn't. So this is the mode structure when alpha is equal, the angle alpha is equal to 0. So I'm not sure I have I put the wrong one here. So alpha is the amount by which I twisted the triangle. So when alpha is 0, this thing goes back to the untampered Kagame lattice. And we have the straight line of 0 modes here, and the dotted lines or the dashed lines are those with the untwisted lattice. When I twist the lattice, I lose all the 0 modes here, and we get a structure which is that of the straight lines, and we get you know, a set of modes that look surprisingly like oh dear. Okay, so this is alpha equals 0, and then I know what it is now. Alpha equals 0. The non-alpha equals 0 part right here, the straight lines, are for a lattice that has next nearest neighbor interactions, So they gap the spectrum right away, whereas when alpha is greater than 0, we get the same thing. In other words, turning on a twist has almost the same effect on the bulk spectrum as adding next nearest neighbor forces. Of particular interest for us, though, is what happens when I go from, shouldn't have, well, anyhow, for this one, the blue line represents what happens when, in the undistorted Kagame lattice, and the dotted lines are what happens in the distorted lattice. And so this is looking at what happens as I go along the line at the end of the Brillouin zone from K to M back to K. And it has this knife structure. When I turn on the twist, it gaps. And those of you who are in the H-bar community know that this is exactly what happens to the Su-Schrieffer-Heeger model, which is one of the first models to show topologically protected zero modes at surfaces. Okay. So the elasticity of the Kagame lattices we can look at now. There are three Q equals 0 states of self-stress are needed to completely stabilize the elastic energy. The Kagame lattice has all of the, it has lots of states of self-stress, so it's in no trouble. It has a full, it's fully stable, and it has lambda equals mu. I was going over my notes. It looks like I changed my mind as to what K was. You'll find a root 3/8 in some of the notes. I have to go back and check to see why there's a difference. Now the twisted Kagame lattice, on the other hand, has two zero modes and two states of self-stress, one guest mode and one bulk mode. So if I look at the elastic energies calculated from the twisted Kagame lattice, we find that B is equal to 0. In other words, B, which is lambda plus mu in the two-dimensional system, lambda equals minus mu, B is equal to 0. So any distortion where ux is equal to minus uy will give me 0. I'm sorry, it's the other way around. So if ux plus, if ux is equal to uyy, this is 0. Uxy is 0. This is 0, and this, of course, is non-zero, but it has 0 energy because the B is 0. So the twisted Kagame lattice has two modes, two non-zero modes. Actually, the other way around. Two zero modes, uxy is equal to 0 and uxx is equal to uyy. And what this does is it gives me a Poisson ratio. Recall the Poisson ratio was the ratio of minus the perpendicular component of the distortion of the lattice over the extension. And this says sigma is equal to -1, which tells us that you have when you pull like this, the lattice goes like that. And I will take the trouble to show a couple of pictures of those in detail in the next installment.
We have
I
a
think
question, Tom.
Oh, okay, here.
We have a question, just a minute.
Yes?
Sorry, was that statement about the Poisson ratio for specific twist angle? Or is that
Excuse me?
did you have a particular value of alpha?
This is this shows what happens as I go along with alpha. You know, alpha gets bigger from here to here to here. So in any one of these twisted lattices, I will have a guest mode, which is to go to the next step. So the guest calculation I showed you was infinitesimal. Basically, you know, it's a linearized limit. These are clearly no longer linear. I'm not in a linear regime. But each one of these is a twisted Kagame lattice, and it has the infinitesimal one. So you can construct the full distortion by going step by step.
Okay, thank you.
Does that answer the question? So this is the
We have
guest
another one there. We have another question there. Just a minute.
Okay. Sure.
Professor, you have energy functionals for your elastic systems. You could consider the thermodynamical behavior of these systems, this kind of lattice system. Do you expect something strange, something different from normal thermodynamical behavior and the effects of the anisotropy on the thermodynamical behavior?
So yeah, my audio connection is not ideal. I mean, it's okay, but I'm having trouble understanding the words there. Can you?
I think the question in general,
Can you repeat? Maybe I can get it.
If you expect any different thermodynamic behavior for these lattices.
Or what's the last word?
Say that.
I think
is the
about
last word?
you have an isotropic general, an isotropic lattices. You have a partition of function.
What is the last word?
If you have elastic energy for
Yes.
the lattices, you could write the Boltzmann factor and study the thermodynamical behavior, equilibrium, in thermal equilibrium.
Okay, all of this is T equals 0.
I know that is that classical treatment. I'm a little further of the question. Like transition phases, specific head, all those physical properties related to the equilibrium of thermodynamical systems.
I wish I spoke Portuguese.
So no, he's asking if you expect some amazing anomalous thermodynamic properties.
Oh yes.
If you study those in those lattices.
I'm sorry about my English.
I understand that. So yeah, there has been some work we did with Xiaoming Mao, others. Asked the question. We particularly looked at it for the square lattice. I haven't done it for the Kagame lattice, but the square lattice has the same problem. You know, you can distort it with zero energy because it has only straight lines and bonds. And there is a point, you know, where the dn equals n0, and you turn on the temperature, and it gives you a temperature dependent, it restores the rigidity, it gives you a temperature dependent elastic constant, which is the, you know, one of them the square lattice by itself only has, it cannot be, it has a zero mode for the shear, the pure shear. And if you go to the site, yeah, let's see, what did we do? We added next nearest neighbor forces, I think it was. And so you can look at a phase diagram and the temperature amplitude of the next nearest neighbor forces. And the point where the next nearest neighbor forces go to zero is in fact the square lattice by itself. And you can do a calculation based upon the Khmelnytsky calculation of stability of, I forget which lattice it was, but that you know, there he has a lattice in which there is a zero energy, zero response running around in your dynamical excitations. And through that calculation, which was used for the smectic liquid crystals, I think. I forget exactly which one it was, but anyhow, it's true that the temperature will give you a missing elastic constant. There's zero in this treatment at T equals 0. There's a paper by me and actually, I forget the name of the postdoc we had, who's Mexican actually. And if you send me your email address, I can send you the reference on it if you like. Okay, did we communicate then? Are we?
Sounds good, Tom.
Yeah.
Okay.
We are actually running out of time, and then it's 11 already. I would like to ask you a question. I think it's a quick question. Those modes that you have shown us, it seems to me they are extended, especially extended. Is it a property of the modes? Do you know the properties of the modes of those guest modes in general? Are they all extended? Are they quasi-localized? Is it known?
They all have this property that if you that they will take you to another state, and you haven't changed the fact of the Maxwell counts, so you can distort them all the way around. So I will probably show a movie that Xiaoming and her crew made, which shows that you can distort the lattice and move zero modes from one end of the sample to the other end always. So it's continuously, or you can keep on going and come back to the beginning.
Okay.
Well, of course, in real systems, what eventually happens is the bonds touch each other, and you can't go all the way around. But until the bonds actually touch, you're okay.
Okay, nice.
So, right.
Is there any
Okay.
other question? Okay, we have another question.
Hi, Professor. Thank you very much for the nice lecture. I was wondering if you can study those lattice distortions, for example, in the Kagome lattice, employing the von Neumann entropy. And if so, what kind of additional information can you get by studying these entropy changes when you distort the system?
So you used what kind of entropy did you say?
The von Neumann entropy, which
Maybe
essentially is giving, it's for zero temperature, and it's given by the density matrix of the system. I don't know if it can be applied in this case.
I actually I am not too familiar with that. I should be. So it's the. I still didn't get the modifier. What entropy is it?
It's called the von Neumann entropy.
The Neumann. Spell it.
Yeah, it's
Neumann?
VON space.
So I guess I don't know the answer because I don't know what it is exactly. So maybe there's something there to do. I mean these are really fascinating systems. Yeah.
Okay, thank you.
Yeah.
Okay, just one more question.
Oh, Professor, if I get it right, you get, if you distorted the lattice, you got those topological protected like phases.
Oh,
but I mean,
yeah,
I mean, you need to change your reference lattice to get those, or how you get that?
Well, I'm still using the Lagrange language, but of course we are doing, the reference lattice is whichever one you want to start with. So for example, I could use in the picture shown now, I have 3 different distorted states. I could take any one of them and call it a reference lattice and then move relative to it.
So, but then, I mean, some of them will display like a topological protected behavior. But I mean, because when you have like, in my mind, right, when you have topological protected states, if you have like slight changes in the positions, you won't get to a topological state for that kind of behavior.
It turns out that I think I've got your question. So the original Kagame lattice doesn't have any of the 0 modes and things like that.
Yes.
It is a critical state separating 2 different topology classes. I can either distort this way, and there are lots of other ways I can distort. So, out of this whole zoo of possible structures, there are critical ones where we get these sample traversing states of self-stress, which then give you, change the elasticity. But the minute you move off of this, so, if I do an infinitesimal step from the original Kagame lattice to the twisted one, then if I go to small enough values of the energy or the frequency, I will get a zero mode, right? In other words, these things, have a topological property until they don't, and it's really right up to the edge that you have. So you have these critical separations. It's the analog of the Schrieffer-Heeger state where all of the bonds have the same length and energy. So that's a critical separate that separates having the 0 mode on the right end from the 0 mode on the left end.
Okay, so thanks a lot, Ton, for this very nice talk, and I would like thank for you, everybody.
Okay, thank
See you.
I'll see you tomorrow. I'll hear from you tomorrow.
See you tomorrow. Thank you.
Right. Oh, what's wrong here?